Okay, here we are in the spirit of practice makes perfect, and also I guess kind of showing you that I'm kind of here in the trenches with you. I'm not asking you to do anything that I'm not ready to do myself. So um, you've done the homework problems, I've done the homework problems, and now we're here to talk about it together. So probably the way I would suggest that you do this is I'd probably suggest you kind of go through that syllabus, do the practice problems on your own, kind of sketch out the answers, get a little familiar with the questions, and then we can kind of go through these narrated PowerPoints together, and we can kind of compare our answers as we do so, see how in sync we either are or are not. Let's get going. So these 5 questions, all kind of the same thing. The book gives you a random variable, right? A random variable, remember, is just a random phenomenon that takes some numerical outcome. And so it's going to give us a bunch of these random variables. It's going to ask us for each one, is it discrete or continuous? Remember, random variables can be one of two things, discrete or continuous. Now, this is not a mathematically perfect definition. If you go on, for example, to take a calculus-based probability class, oh man, don't use this definition there. You'll get us both into a lot of trouble. But for Math 121, this is a good enough definition, and it's the one that I'm going to stick with for ease and simplicity and just overall kind of intuitiveness. So, and that definition is, right, if it takes whole numbers, only whole numbers as values, then it's going to be discrete. And if instead of taking just whole numbers, it takes values over an entire interval of values or an entire continuum of values, we're going to call it continuous. So the first one, what's the first one? The first one is, right, some crazy lunatic with too much time on their hands, for whatever bizarre reason, decides to take a coin and toss it 100 times, counting every time whether it's heads or not, and then overall just how many times out of 100 they got heads. So this is an example of a discrete random variable, right? You can get heads 42 times, you can get heads 43 times, but you cannot get 43.23 heads. Agreed? Right? It takes values just in the whole numbers. Number 18, number of people in line at the bank at a randomly chosen time. So we randomly choose a time, we go to the bank, we count how many people are standing in line. This is also a discrete random variable. Right? You can have 2 people in line. You can have 3 people in line. If you told me, oh yeah, there was 2.7 people in line, I'd probably give you a little bit of a funny look, right? Doesn't make sense to say there's 2.7 people in line. And so again, that's what makes this discrete. Keep in mind, right? Anytime I see that like, what are the keywords? The keywords are number of. Right? Number of means we're counting something. Most counting phenomenons, most counting problems. I'm tempted to say all counting problems, but I try to avoid things like that because every once in a while I come up with like a crazy counter example. But certainly most, maybe all, counting problems are going to be discrete in nature. Right? When you're counting something, there could be 1 of it or 2 of it or 3 of it, but generally not 2.7 of it. So what is continuous? Well, weight, that's number 19, right? The weight of a randomly chosen backpack, right? Weight is a very common phenomenon that's conceptualized as being continuous, right? That is, a backpack can weigh not just 8 pounds, not just 9 pounds, but if we have a precise enough scale, it could weigh 8.275 pounds, right? That it's not just 8 or 9, but in theory, it could weigh any value between 8 and 9. Again, assuming we have a sort of precise enough scale to measure it. Amount of rain during our next thunderstorm. Again, that's going to be continuous. We could have 1 inch of rain, 2 inches of rain. But again, if we measure it precisely, it's certainly possible to have, right, 1.3333 continuing inches of rain. And so that makes it continuous. Number 21, the number of children absent from school on a randomly chosen day. Those poor children, they're going to miss out on math class, right? That's there's that keyword, number of. So anytime we're counting something, we're going to think of that as discrete, right? There could be 10 children absent, 11 children absent. Doesn't make sense to say 10.2 children absent. And the last one, number 22, time it takes to drive to the airport. Again, if we have a precise enough stopwatch, it could be not just 30 minutes, not just 31 minutes. It could be right 30.313152975111225912 minutes to get to the airport. We don't normally, of course, record it to that level of precision, but in theory, it could take that amount of time. Again, not just 30 minutes, not just 31 minutes, but in theory, it could be any value over that continuum between 30 and 31. Actually, over a much, much larger continuum, right? All right, so I mean, that's one type of problem, fairly straightforward. The second type of problem is, right, we give you a discrete random variable, and we ask you to calculate the mean or the expected value, right? Those are sort of two terms that mean the same thing, two alternative ways of saying the same thing. Now, this is a type of question that it should be easy, but it can sometimes get students into trouble. Your natural inclination, right, when you see that word mean, it's been drilled into you from grade school, to just see that word mean and start like computing the sample mean, add them all up and divide by n. But you got to suppress that urge, because that urge is going to get you into trouble. The mean of a random variable is different than the mean of a sample, and consequently, it needs to be calculated or computed differently. We'll see on the next slide. So here our random phenomenon is the number of defects in a randomly chosen circuit board. So this is like what? This is a quality control problem. Statistics is used quite a bit in quality control settings. So imagine we have this sort of assembly line, maybe every 100th, every 200th circuit board. We pull it off the assembly line. We take a look at it. We test it. We measure the number of defects. 50% of the time it's fine, it's perfect, there's 0 defects. 30% of the time there's 1 defect. 10% of the time there's 2 defects. Also 10% of the time there's 3 defects. So, right, on average, how many defects do we expect to see, or what is the mean of this random phenomenon? Well, let's go to the next slide and find out. So there's that formula, right? In all its simplistic glory. It's not that hard as long as you put in the work to make sure you remember it for the test. And again, to remember it, just do it. Do the homework problems. Do the examples. That's going to put it inside your muscle memory. And that way it's not going to have to feel like some laborious memorization. If you did the 3 that I already did in the narrated PowerPoints, you do the 2 that are from these slides, and if you do them yourself, write out the numbers, calculate them, verify the math, then it's going to sort of emblazon itself in your spirit. You're not going to have to just kind of do some sort of silly, painful memorization of it. And you're going to get free points on the test. So what's the formula? The formula is, right, we add up the outcomes weighted by their probabilities. And this idea of weighted means multiplied by. So the formula is 0 times the probability of 0 plus 1 times the probability of 1 plus 2 times the probability of 2 plus 3 times the probability of 3. You plug in all those numbers from the previous slide, and there we are, right? It's kind of actually 0 times who cares, right? Because 0 times anything is 0. But we'll be a little bit more polite, I guess. 0 times 0.5 plus 1 times 0.3 plus 2 times 0.1 plus 3 times 0.1. Maybe we do that in our head, maybe we put in our calculator, but go ahead and verify that I'm correct. I believe we get 0.8 for our answer. Now, it's one of the kind of quirks of the mean of a random variable, right? The random phenomenon itself actually can't take the value 0.8, but the mean nonetheless is 0.8. That's not an error. We do not round it up. We would say that the mean is 0.8. So how do we interpret that, or how do we use that? Well, a lot of times the mean is more useful when we're kind of thinking about random phenomenons in like the long term. So like imagine a situation, I don't know, where maybe we manufacture 1,000 circuit boards in a given day. Any one circuit board, we say we expect 0.8 defects. So it would make sense, hopefully, to say if we made 1,000 circuit boards, we would expect 0.8 times 1,000. If you put that in your calculator, you get 800 defects. Now it's feeling a little bit more intuitive, right? And also now we're glad we didn't round, because that if we rounded up to 1, now we're saying we expect 1,000 defects, but the truth is really just 800 defects is what we would expect. Why do we care about this? Well, again, right, if we want to budget, if we want to set aside money, if we want to clearly anticipate impending costs, we could maybe associate a cost with each defect, say maybe $2. And we can say, okay, well, on a given day, we expect 800 defects. It costs us $2 a defect. So we want to make sure that we allocate $1,600 a day to kind of fixing or clearing up defects in our circuit boards. Right? That allows us to sort of do good, proper planning. It allows us to anticipate, right, what's coming down the road and then be able to kind of handle it or deal with it. Wow. Thanks, statistics. So one last example, though I kind of bet by now you don't need it. In fact, I would recommend, I mean, if you had problems with that one before, I'd recommend pausing these narrated PowerPoints and solving this problem yourself. That is, right, pause it and calculate that mean right there. That's what it's essentially asking. So we have this random phenomenon X. It's the number of days in a given year. In which some air pollution limit is exceeded. So right here's that probability distribution. Most of the time we have a perfect year. I guess, well, I shouldn't say most of the time. 33% of the time, right? 0 days exceed the limit. So right, that would be a perfect year. 38% of the time, right? 1 day is bad. 19% of the time we have 2 days out of the year that are bad. 6% of the time we have 3 days. 4% of the time we have 4 days. And apparently in this situation, we've never had a year that's had 5 or more bad days. So on average for a given year, how many days do we expect to see exceed these limits? Well, again, if you haven't calculated it already, pause it and calculate it yourself, and then you can go to the next slide. I'm going to go there in just a second, and we can compare our answers. How'd you do? I got 1.1. I have a good hunch. I have a good feeling that you got the same thing, right? Again, 0 times the probability of 0 plus 1 times the probability of 1 plus 2 times the probability of 2 plus 3 times the probability of 3 plus 4 times the probability of 4. Plug all those numbers in, double check my math, and hopefully we should get 1.1, right? So we would say in any given year, we would expect 1.1 days to be in violation of whatever these pollution standards are. Yeah, pretty simple, right? And hopefully with a little extra practice behind us, it's going to set us up. It's going to set us up for an even higher level of success when we go ahead and take our eventual exam on this material. So good job.